Hello everyone. In today's video, we will be learning some must-do questions of binary search. In the previous two videos, we have discussed some must-do questions of bit manipulation, and before that, we have discussed the questions related with the number theory, like how will you find a primary number, okay, and how will you find the factors, how will you find the factorial, and that's all, okay. So today we'll start with binary search. Okay, so binary search is a two-pointer approach. Okay, and this approach will always be applied on a sorted data structure. Okay, and if you have sorted data structure, then after seeing that thing, there should be two things which should come in your mind. The first thing, can I apply a binary search here? And the second thing, can I apply two pointers approach here? Okay, so today we will be starting with the binary search. Okay, so let me tell you this algorithm first. So let's suppose you have an array. Okay, give me a second. Okay, you have an array. Let me select the draw. All right. Initially, you have an array, and let's suppose that array is 1, 5, 9, 11, and 15. Okay. And what you have to do, you have to search for an element. Let's suppose the target element. Let me give the target equals to 11. Uh, So what will happen? See, initially you know this thing that your array is sorted. You have sorted data, and if you know the basic concept of searching, so you must know the basic approach of searching by linear fashion. That is linear search. If I have 1, 5, 9, 11, and 15, so what will I do? I will start my searching from the index 0, and I will check at any point is my array of I is equals to target. If yes, simply return me this index. Okay. So this was the naive approach. Okay, this is a naive approach, and this approach will take a time complexity of big O of n. Why big O of n? Because what in the worst case, what you are doing, you are starting from the zeroth index and moving till the last index and searching the corresponding target index by index. Okay. Uh, but why binary search is an optimal approach? Because binary search will always take you the time complexity log n. That means if this program is taking 10 milliseconds to run, then this program will take 1 milliseconds to run. Less than 1 milliseconds to run. Okay. Why it's taking log n? Let's begin with the approach. So in binary search, what we do, we take the help of two pointers. Okay. The first pointer will be your low, that will be initialized with 0, and the second pointer will be your high, that will be initialized with the last index of your array. What will be the last index? The last index will be array dot length minus 1. Why? Because the total length is 5, so the last index will be 4, because in array the indexing starts from 0. All right. So uh, now what we do, we take a mid variable, and that mid is equals to low plus high by 2, and that will be a corresponding value which will be the index. Okay. So what we will do initially, let me dry run it for you. Uh, let's The array will be 1, 5, 9, 11, and 15, and what I have to do, I have to search for target, and that target is initially 11. Let's search that. So first what we will do, we will find the mid, and the mid will be 0 plus, and the last index will be 4. 0 plus 4 by 2, that becomes 2. So my mid index is equals to 2. So the very first thing that I will check is my current mid is equals to the target. If it is, just return that mid. If my array of mid is equals to target, that means I got my answer. In that case, simply return mid. But what if, but what if the current value of my mid is greater than the target. That means you are at value which is greater than your target. So can I say this thing? Can I say this thing? If you are searching from 1 to, if your mid is 9, initially you are at mid. So 0 plus 4 by 2 becomes 2. 0, 1, 2, 9 will be the element which is at mid index. So can I say this thing? If this 9 is greater than target, if this 9 is greater than 11, so I have to search in this part. But if this 9 is less than 11, then why will I be searching in this part? Because I know this thing, the all the parts are equally shorted. So can I say this thing? If the left part, if in the left, if I'm at the element which is less than the target, so my answer cannot lie to the left of it, because the left elements are already less than that. So I will be searching in the right part. And if my current mid is greater than the target, so that means I have to search in the left part, because if my mid is greater than the target, so the leftmost part are always less than the mid, so my answer can lie in the left part. So I will be searching in the left part. Okay, so how will I move to right and left? If my middle element is greater than target, so I will be searching in the left part now, because if mid is greater than target, so there may be possibility that less than mid can be equal to the target. So in that case, what will I do? I will simply put my high pointer to one step ahead of mid. That means if I have searched till now, then I will be searching from here to here. This will not be included. So high is equals to mid minus 1, and else if my mid is less than target, so I can say this, the left elements of my mid cannot be my answer, and I have to search in the right part. So to move towards the right part, I will make my low pointer to mid plus 1. All right. And at last, I will be returning the mid, because at last I will get an element where my mid is equals to the target, and I will be returning that mid. So that's the basic approach of binary search. And what's the approach? Find the mid and search for if your mid is equal to target. So that means your mid is your answer, and if your mid is greater than the target, that means you have to search in the left part. And if your mid is less than the target, that means you have to search in the right part. Okay, so let me show you the code for that. Okay, and this is the code. Okay, so what I did, there were two pointers initially. First, there will be a start pointer, and second, there will be an end pointer. Okay, and start, and the condition should be, we all know this thing. The initial value cannot be greater than the final value. Okay, so in while loop, there will be a condition that my start should be always less than or equals to end. That means my two pointers cannot exceed their values. End should not be greater than start, because every time what I'm doing, I'm changing the position of my start and end with respect to the mid. So there may be a possibility that I end up getting a index where my start is greater than end. So I have to counter this condition. So initially my mid will be equals to start plus end by 2. And after that, if my mid is equals to target, that means I got my answer, and in that case, my mid index is the answer. Else if my mid is less than target, so can I say this thing? Why will I be searching in the left part? I will be searching in the right part. And if my mid is greater than target, then why will I be searching in the left part? I will be searching in the right part. That's it. And if I'm not able to find any answer, so there may be a possibility now that your target is not present in your array. You are searching for an element which is not already present in your array. So can I say this thing? You will be returning minus 1, because you haven't found any mid element. You haven't found any element which is equals to your target. So I will simply return minus 1. That's it. Okay. So now let's move towards the next question. Okay. The next question is your peak element. Okay. This one. So what do we mean by peak element? Okay. All right. So what do you mean by peak element? So this question is also based on modified binary search, or you can also say that this is the extension form of binary search. Okay. So what do I mean? Let's suppose you have an array. Okay. And that array is ARR is equals to 1, 3, 4, 5, and this will be your 2. This will be 1, and that will be your 7. What you have to do, you have to find the element which is the peak element in this array. So what do I mean by peak element? So we all know the concept of mountains. So in the case of mountain, so the topmost point is always called as the peak of that mountain. Why we call it peak? Because the leftmost part of that mountain and the rightmost part of that mountain is less than that point. That means the left part will always be less than this point, and the right part of it will always be less than the topmost point. That's why we call it a peak point, which will be always greater than the left part of that and the right part of that. Okay. So you have to find an element in this array which is a peak element. So let's start with the 3. So in the left side of 3, there should be less than 3, and in the right side of 3, there should be less than 3. So in the left of 3, there is 1. Yes, it is. The condition is true because 1 is less than 3. But in the right side of 3, there is 4, which is greater than 3. So that 3 cannot be my peak element. Moving towards the next, let's go with 4, 3, and 5. So in the case of 4, 3 is less than 4. The first condition is true, but 5 is not less than 4. So it will be false. So 4 cannot be my peak element. Let's go with 5. To the left of 5, we have 4, and to the right of 5, we have 2. 4 is less than 5 and 2 is less than 5. Yes, I got my peak element. I will be returning this 5 as my answer. So how will I be doing this thing? So the concept will be same. There will be a low pointer which will be at 0, and there will be a high pointer which will be at the length minus 1. Okay, and there will be a mid. Okay, and that mid will be equals to low plus high by 2. Okay, and what you will be doing? Can I say this thing? Can I say this thing? If if your mid is pointing any point, let's suppose your mid is at index number 2. So can I say this thing? If your mid is greater than mid plus 1, so can I say this thing? This mid can be your peak element. If your current mid is greater than the next mid, sorry, if your current mid is greater than the next element, so can I say this thing? This mid can be your answer. And now you have, so now the right condition is being fulfilled. Now you will check in the left part, because the right condition is fulfilled. So why you will be searching in the right part now? So you will be searching in the left now. So can I say this thing? If you will search in the left, your high will be equals to mid, because initially your high was here, but now you will be searching from here to here now. So your next high will be equals to mid and your low will be here. So you will be searching in this part only now. But what if your mid is not greater than mid plus 1? That means your mid is less than mid plus 1. So can I say this thing? If your mid is less than mid plus 1, that means your mid plus 1 can be a peak element because the left part of it is less than the mid plus 1. Now you have to search for the right part only. That's it. That means if your mid plus 1, if the next element is greater than the previous element, so can I say this thing? The next element can be your peak element because the left of it is less than that. So now you have to search in the right part only. So to search in the right part, can I say this thing? Now your high will be here only and your low will be here. That means you will start searching from the mid plus 1. That will be low is equals to mid plus 1, and you will search from here to here, and at last there will be a point where your low pointer is equals to your high pointer. So in that case, you can either return low as your answer, or you can either return high as your answer. So let me recap the things again. The first thing will be what you will be doing. You will be finding the mid, okay? And before that, you will be taking a low pointer that will be 0. And after that, there will be a high pointer which will be length minus 1. All right. And you will be taking your mid that will be low plus high by 2. And after that, what you will be doing, you will be checking is your mid, is the element which is present at mid index is greater than mid plus 1 index. If yes, then you got one of the condition and your mid can be your answer and you have fulfilled the right condition. So you will be searching in the left part. So next, so for this, your high will be equals to mid. And if your mid is less than mid plus 1, so can I say this thing? Now, one of the condition is fulfilled and your mid plus one can be a peak element. So now you will be searching at the right part. So now next, your low will be equals to mid plus one. And at last, I told you this thing, you will end up getting a condition where your low is equals to high. So in that case, either you return low as your answer, either you return high as your answer. You can even either return any of the values, but we always return the low pointers only, okay? Because that's the basic programming rule. Always go with the smaller values if you're getting the answer correctly. Okay, so let me show you the code. Okay, so what I did, there were two pointers initially. The first pointer was low pointer, and the second pointer was high pointer. And after that, I made a condition that my low should be less than high. I told you in the previous question that my low pointer should not be greater than the high pointer because the initial value cannot be greater than the final value, or the final value cannot be less than the initial value. Okay. So next time then we will be taking mid. Mid will be equals to low plus high by 2. Why I did this high minus low by 2? Because there may be a possibility that low is a very minimum value and high is a very large value. So in that case, your mid will be a very large value. So what I did, I write low plus high minus low by 2. So that will be a smaller value after that, and you will be getting the same answer. So if the element which is present at the mid index is greater than the mid plus one, so in that case, what will I do? I will simply search in the leftmost part because the right condition is being true. So my high will be equals to mid, and else if my mid the element is which is present at the mid index is less than the element which is present at the mid plus one index. So in that case, what will I do? I will search in the rightmost part because mid plus one can be my peak element and the left part is already satisfied. And at last, my low can be equals to high because I will end up getting a condition where my low is equals to high. So in that case, what will I do? I will simply return this low index. You can either return low, you can either return high. It's up to you. But with the basic programming rule, I'll always go with a lower corrected value. So that will be I will be returning low. Okay. So let's move towards the next question. So in this question, what you have to do, let me read that question for you. You are given a sorted array consisting of only integers where every element appears exactly twice, except for one element which appears exactly once. Return the single element that appears only once, and your solution must run in big O of log n time and O of one space. So what does it mean? See, what you have to do, you have to find that element which appears only once, and this is your sorted array. Okay, the array will be sorted, and what you have to do, you have to find that unique element which appears only for once, and every other element except that element appears twice. So what you have to do, you have to find that element, but there is a constraint that you cannot exceed the algorithm. All right. So, except that there is a catch. You cannot exceed your logic. You cannot exceed your algorithm by log and time complexity. Okay. So the naive approach will be you'll be starting from the zeroth index. Okay, and you'll move till the last index, and you will be checking that if your nums of I is equals to nums of I plus one. If it is, that means you have to move your I pointer one step ahead, because that cannot be your answer. But there will be a condition where your nums of I is not equals to nums of I plus 1. So that will be your answer. But this approach will take you big of n time complexity. Okay. So how we're gonna optimize it? So to optimize it, we'll be using binary search, because I told you this thing. If your data is sorted initially, so you can use two things initially. The first thing, you can use binary search, and the second thing, you can use two pointers approach. Okay, so we will be applying binary search here, because the data is already sorted, and the time complexity of binary search is log n. So we will be moving with log n time complexity. Okay, so let me tell you the approach. Okay. So what will be the approach? Okay, so suppose you have an array. So suppose you have an array, and that array is 1 1 2 3 3 4 and 4. So the array is sorted initially, and you know this thing that you will be applying binary search. Okay, and there will be a low pointer which will be initialized with 0, and there will be a high pointer which will be initialized with the last index of your array. That means 0 1 2 3 4 5 6. Okay, the total length is 7, and the high will be 6. Okay, the mid will be equals to 0 plus 6 by 2, and that will be 3. So can I say this thing? Can I say this thing? Uh, your element, your the element which appears only once will always be at odd index initially. So what do I mean by odd index? Let's suppose uh, your mid. Okay, let's suppose your mid is at 2, mid is at 3, and I know this thing. 3 is an odd number. So in that case, what you will do, you will simply decrement your mid value by 1. Why I said this? Because let's suppose the third index will be 0, 1, 2, 3. This will be your 3. Okay. So why I'm decrementing mid minus 1? Because I know this thing. If I am at the odd index, then that index, if I am at the odd index, so that index cannot be my answer, because every element is appearing twice, and there is only one element which appears once. So it will always be present at the even index, because I'm starting my indexing from 0. So in simple words, I can simply say this thing: my first element, या फिर my the unique element will always present at the even index, because I'm starting my searching from the zeroth index. Okay, so if I'm at the odd index, I will decrement my mid with minus 1. I will decrement my mid with 1, because I know this thing: my answer will always lie at the even index. Okay. So if my mid is at odd index, so I will simply decrement my mid by 1. In the second case, if my nums of mid is equals to nums of mid plus 1, what does it mean? Let's suppose you are at a number 4 comma 4, and this will be 5 5, and so on. So can I say this thing: if your mid is at this position and mid plus 1 is at this position, and you know this thing, your mid is equals to mid plus 1. So can I say this thing: you will start searching by skipping the second index. What does it mean? If you are at 0 1 2 3 third index, you know this thing, at the fourth index you'll also get the same element. So can I say this thing: after third, you will start your searching from the fifth index, you will skip this index. So in that, so skipping condition will be equals to low is equals to mid plus 2. You have skipped that element and start searching from the rightmost part after skipping that element. And if it's not equals to mid plus 1, and if it is at the even index, so what you will do, you will start searching in the leftmost part, because I just said this thing: if you have if your mid is at the odd index, let's suppose 0 1 2, if your mid is at this position, if your mid is at this position, so you will be searching from here to here, this from this to this, and you will end up getting that answer which you need. Okay, so your high will be equals to mid, and at last, what you will do, you will be returning. So every time what you are doing, you are increasing low and high, And there will be a case where your low will represent your answer. Your low index will be your answer. Okay, and that low will be equals to, let's suppose low will be equals to 2, and 2 is the index where your element is present, which is appearing only for once. So in that case, what you will do, you will be returning nums of low in your answer. All right. So what's the logic? uh, If your mid is present at the odd index, decrement it by 1, because your answer will always be at the even index, because every element is appearing twice and that's the element which appears only once. Okay. And if your mid is equals to mid plus 1, that means here the previous element is equal to the next element. So you won't be searching the next, because the element is same. So you'll start searching by skipping that element. The skipping condition will be equals to low is equals to mid plus 2. And if you are at the even index or your mid is not equals to mid plus 1, so in that case you will be searching in the leftmost part, because this will be the section where your answer lies. Okay. And at last, your low pointer, you can dry run it. Your low pointer, the low pointer will present at any index, and that index and that element which present at that low index will be your answer, will be the element which appears only for once. All right. So let me show you the code for that. Okay. So initially I have taken a low pointer. Okay. That will be equals to 0. And I have taken a high pointer, that will be the last index of my array. That is nums dot length minus 1. And the condition is same. Your low should be always less than high, because your initial pointer cannot exceed the high pointer and your high pointer cannot decrease by the low pointer. Okay. And after that, you will be taking your mid is equals to low plus high minus low by 2. Why I did this? Because I told this in the previous questions too. Like your low can be a very minimum value and your high can be a very large value. So so at last you will get you will get a mid which will be a very large value. So just to deal with that condition, what will I do? I will use high minus low by 2. Okay. Second, what will I check is my current index, the index at which my mid is present is at odd index or an even index. If it is at odd index, so what will I do? I will decrement my mid with 1, because I know this thing, my answer will always lie at the even index. Second, you will check that your mid is equals to the mid plus 1. That means the element which is present at the mid index, is it equals to the element which is present at the mid plus 1 index? If yes, then you can skip the next part, because the next part will be the same. So low will be equals to mid plus 2. And if your mid is present at the even index and your mid is not equals to mid plus 1, so in that case what you can do, you will search in the leftmost part, and at last the the index on which your answer will be present, that will be your low index, and at last you have to return the element which is at the low index. Okay, so I will be returning nums of low. And you can do one thing, you can try run it. Okay, because the writing the brute force and writing the naive approach, and after that you'll have to write the optimal approach. So just to deal with all the conditions, so you just have an habit of dry running. Okay, like take an array, start the index from the low pointer, and take the high pointer at the last index of your array, and dry run it. Okay, take out the mid. Okay, check the condition that it is available at the even index or an odd index. Okay, then check for equality, and then check for a condition where your mid is present at the even index and your mid is not equals to mid plus 1. So that can be your answer. And there will be a condition where your low pointer will be at a position where your element which appears only for once lies there. So what you will do, you will simply return, or you'll simply return that element which is at the low index, that will be nums of low. Okay. So till now we have discussed three questions. The first question was the basic binary search. The second question was lead code medium level challenge. Okay, that was a find peak element. And after that, we have discussed single element in a sorted array. Both all the above questions, all these questions are the basic and must-do questions of binary search. And binary search is an optimal way of searching. which takes you in log and time complexity. And that's an optimal approach of solving and searching, and it always applied on a shorter data structure. Okay, so that's all for today, and thank you.